This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on logarithms. So to remind ourselves of the basic notation, if we say log base 2 of 8 equals x, the base is the base of an exponential expression. So the base is this 2 to the x equals 8. The answer is an exponent, the base is the base. So 2 to the x is 8. 8, of course, is 2 to the third power, and x is 3. If I use just log, so I have log 10,000 is y. If we use log, that means log base 10. So log base 10 of 10,000 is y. The base is 10, the exponent is y. 10 to the y equals 10,000. But 10,000 is 10 to the fourth. 10 to the first is 10. 10 to the second is 100. 10 to the third is 1,000. 10 to the fourth is 10,000. So we get 10 to the y is 10 to the fourth, and our exponent, our answer, y is 4. But our favorite logarithm is the natural logarithm. So the example I'm going to use here is the natural log of the square root of e is going to equal z. If we write natural logarithm, that means log base e. So we have log base e of the square root of e is z. Rewriting the square root of e as e to the 1/2, we have log base e of e to the 1/2 equals z. The base is e, the exponent is z. E to the z equals 1/2, z is 1/2. So log base 2 or log base b, log base 10, log base e, these are various cases that we're going to look at. Now there's relatively few rules in the world of logarithms, but you need to study those fairly well and know them. Log base b of mn is log base b of m plus log base b of n. We say the log of the product is the sum of the logs. Regarding quotients, m divided by n, log base b of m divided by n is log base b of m minus log base b of n. The log of the quotient is the difference of the logs. Log base b of m to the r, we can pull the exponent down, that's r times log base b of m. And maybe that's obvious from this first rule. If I have log base b of m times m times m times m, r times, I would have r log base m's here, or r times log base b of m. And finally, we have this change of base rule. Log base b of x can be thought of any other logarithm. Typically, we use natural logarithm, but log of x divided by log of b. That's one way for us to convert from one scheme to another in the world of logarithms. But it's a very nice tool for solving equations and rewriting mathematics expressions. So let's look at this one. You want to rewrite log base 5 of 25x squared over y cubed z. So we're first looking at log base 5 of that statement. Log base 5 of the quotient is the difference of the logs. So the log of the top minus the log of the bottom, with the same base, of course. So log base 5 of the top minus log base 5 of the bottom. But the log of the product is the sum of the logs. This will be log 5 of 25 plus log 5 of x squared minus quantity log base 5 of y cubed plus log base 5 of z. So that's using our product rule. Now log base 5 of 25, 5 to what power is 25? That, of course, is 2. This thing we can pull the exponent down, 2 times log 5 of x. Pull the exponent down, 3 times log base 5 of y. So we get this rule, and all we have to do now is distribute the minus signs, and we've written this in expanded form. So this original statement is equivalent to this statement using the properties of logarithms. But our favorite tool for logs is to solve equations. So let's go ahead and rewrite that first. And this is what I wanted the original equation to be. 2 to the x plus 3 equals 7 to the x. We want to move the exponents down, so to do that we're going to take the natural logarithm of both sides. We'll take log of 2 to the x plus 3 equals log of 7 to the x. So doing that, we're here, and now we can pull the exponent down. X plus 3 quantity times log 2 equals x times log 7. Next move is to distribute x log 2 plus 3 log 2. And we get that. And we want to get all of the x's on the same side. The simplest thing would be to subtract x log 2 from both sides. So I'd have 3 log 2 on the left side and x log 7 minus x log 2 on the right side. Next, we're going to just factor this x. Factoring the x, we get x times quantity log 7 minus log 2. And then to solve for x, we're going to go ahead and divide by log 7 minus log 2. And we get 3 log 2 divided by log 7 minus log 2 is x. Remember, my original question was 2 to the x plus 3 equals 7 to the x. Hitting it with a log enables us to solve for those exponents. Okay, the next example I have here is log base 2 of x plus 1 plus log base 2 of x minus 5 equals 4. Now before we get started, let's remind ourselves of the domain of a log function. The numbers in the parentheses must be greater than 0. The domain of any log function, the argument, must be non-zero numbers. So x plus 1 has to be positive. X minus 5 has to be positive. Well, if x minus 5 is positive, x has got to be bigger than 5. Over on this side, x has got to be bigger than negative 1. Well, regardless, my answer has to be something larger than 5 to be in the domain of this function. So how do we do this? We're going to appeal to our rule. The sum of the logs is the log of a product. So this is going to be log base 2 of x plus 1 times x minus 5 equals 4. And then we'll need to multiply that together. So that's x squared plus 1x minus 5x, x squared minus 4x minus 5, I believe. And that's 2 to the 4th. Remember, there's our base. 2 to the 4th power is going to equal x plus 1 times x minus 5. 2 to the 4th power, 16, is going to be x squared minus 4x minus 5. Subtracting 16 from both sides now, what are we going to get? 0 is x squared minus 4x minus 21. Factoring this, x minus 7 times x plus 3. So x minus 7 is 0, or x plus 3 is 0. If that's the case, we get x is 7, or x is negative 3. But remember our discussion on the domain. X has to be greater than negative 1. X has to be greater than 5. Negative 3 is not greater than 5. Negative 3 is not in the domain, but 7 is. We can do a little quick check. 7 plus 1 is 8. Log base 2 of 8 is 3. 7 minus 5 is 2. Log base 2 of 2 is 1. And 3 plus 1 is 4. So that checks. Negative 3 not in the domain. Negative 3 cannot be our solution. So since negative 3 is not in the domain, our only answer is going to be 7. We also like logarithms to help us find values of inverse functions. So if I'm looking at f of x equals 3 to the x, I want to find f inverse of x. What is f inverse of x? Well, our general strategy was to rewrite a function this way as y equals 3 to the x, and then switch the x and the y. So x becomes y becomes x. Now I have x equals 3 to the y, and your goal is to solve for y. To do that, I'll hit both sides with a natural log. So natural log x equals natural log 3 to the y. Let's pull that y exponent down using our property of logs. So we'll say log x is y times log 3. Then dividing by natural log of 3, we get y is natural log x over natural log 3. That is the inverse. I could say that. But I could also recognize the fact that natural log x over natural log 3 is log base 3 of x, using our first rule, our change of base formula. So both of these work as f inverse of x. So I could argue that f inverse of x is log x over log 3, or I could say f inverse of x is log base 3 of x. They're both the same. But you'll notice the inverse of 3 to the x is log base 3 of x. You see how the original function and the logarithm are related in terms of getting their inverse. Okay, let's take a look at another one. Here I have f of x is 2 plus 5 to the x plus 3. And again, I want to find f inverse of x. So we're going to change f of x to y, and then x becomes y becomes x. Rewriting it that way, we now get x equals 2 plus 5 to the y plus 3, and our goal is to solve for y. Subtract 2. X minus 2 is 5 to the y plus 3. Now to pull an exponent down, our strategy is to hit it with a logarithm. Log x minus 2 equals log 5 to the y plus 3. Y plus 3 comes down front. We get log x minus 2 equals y plus 3 times log 5. Our next move will be to distribute. Log x minus 2 will be y log 5 plus 3 log 5. So you'll notice that. And then our strategy requires us to solve for y, so we'll need to subtract 3 log 5 from both sides. So log x minus 2 minus 3 log 5 will equal y log 5. And I want to solve for y, so I will divide both sides by log 5, and that will result in log x minus 2 minus 3 log 5 over log 5 equals y. That will be my f inverse of x. We've gone through that process, and we have now concluded that f inverse of x is natural log x minus 2 minus 3 log 5 over log 5. Let's take a quick look at an example. We want to take a look at exponential growth and decay. We have an investment of $1,000 is made in an account that is compounded continuously. 8 years after our initial investment, there is $1,200 in the account, and we want to find the yearly interest rate. Well, to be able to do this, we need to know our formula for continuously compounded interest, and that is A, the amount on account, is P, principal, times e to the RT. And I want to find the interest rate, so I'm looking for R. Now, what are the other variables that I'm given? The amount on account is $1,200. Principal, the original investment, is $1,000. And T in years is 8. So we have all of this information, and we can plug those values in to solve for R. That's what we're looking for here. So using that, making our substitution, it will be 1,200 equals 1,000 e to the R times 8. Of course, R times 8 is 8R. No major change here. Dividing both sides by 1,000, 1,200 divided by 1,000 is 1.2, or 6/5. So we get 6/5 is e to the 8R. To solve for the exponent, we are going to hit both sides with a log. We'll take natural log of 6/5 is natural log of e to the 8R. Now, we can simplify this a little bit. You'll remember the log of the quotient is the difference of the logs. So we could say this is log 6 minus log 5. Over on this side, the 8R comes down in front. So it's 8R times the natural log of e. So again, you'll notice log 6/5, log 6 minus log 5. And then pulling the 8R down, we have 8R times the natural log of e. But the natural log of e is just 1. E to what power is e? The natural log of e is 1. E to the first power is e. So we get log 6 minus log 5 is 8R, and you can see we've just about solved for R. We're going to go ahead and divide both sides by 8. And we get log 6 minus log 5 over 8 gives us an R of 0.023, or 2.3% per year. And that will conclude this lesson.